Hey guys, sorry I'm late. I was in the middle of working on something and lost track of time. You guys there?
Yep.
Okay. Um, before I let you guys start asking me questions, which I suspect you probably have some questions, I want to show you a couple of things having to do with linear regression analysis. I had some conversations with some of you yesterday, and I think I just want to clarify a couple of things on that. I realize that is due today, technically, but I think I want to give you another 24 hours in case something we go through today clarifies things for you so that you have time to go back in and incorporate those clarifications into what you're doing. Does that sound reasonable?
Yes.
Yeah.
Okay. All right. I'm going to share my screen with you. I've been working on my own script for these gecko data. As it turns out, the analysis that I'm asking you to do is not the analysis that I did when I originally analyzed these data. So I've had to go back and recreate, well, build some script from scratch to do the kind of things that I'm asking you to do. So the first thing that I did was I read in my data. And so there's the data file. And you recall that it also has a bunch of environmental temperatures, like tons of environmental temperatures, because I took random samples of the environment, and then wall temperatures. But I've taken these wall temperatures and basically just recreated them in a separate column there. So, of course, the first thing that you have to do is you have to get rid of all of those other temperatures. And so I'll need tidyverse for that, but I might as well, load all of my packages. And then the first thing that I want to do is I want to filter it out so that there's just temperature data from the body temperature. So I've been using summary to give me an idea of what's in my data set. So when you type summary and then you put your data frame inside of there, it tells you what is in your data frame. And so you can see that we filtered out what we could have done. Let's go back up here. Do this and this. Well, rather than scroll through your data set, you could actually just use summary to get an idea. So you have 698 geckos collected during the summer, 697 collected during the winter, 572 of these were from Galveston, 823 of them were from Oklahoma City. The researcher who works on geckos at the University of Central Oklahoma is probably very upset at me that I've taken 823 geckos from her population, but I can't really worry about that. So this gives you an idea, but you see that you have environmental temperature, preferred temperature, and wall temperatures all in here. But we only want the 182 geckos that we have both body temperatures for and wall temperatures for. So that's the whole purpose of filtering this out. And so when we get that, we are left with those 182 body temperature, wall temperature combinations. 82 of them are from Galveston, 100 of them are from Oklahoma City. 112 of them are from the summer and 70 of them are from the winter. So the next thing that I did was I just subsetted this data and I gave myself, good names. So winter OKC. So this is all temperature data. So I just make a bunch of things. And when I want to check them, I don't look at the data set. I just get a summary of the data set and it says I have 40 winter geckos that were also collected in Oklahoma City. Winter Galveston, once again, should just be winter Galveston. So keep track of sample sizes as well. Summer Oklahoma City should just be summer in Oklahoma City. And then summer Galveston is summer Galveston. So now we have 5 different data frames saved in R. We have the original data frame that has everything. Then we have each of these subsets of the data that are subsetted by season and population. Well, we could run an analysis on the full model, and that's a pretty darn good regression. It's highly significant, and it basically is very close to 1, as one would expect when you're combining across all populations and all seasons. A lot of treatment, a lot of effect due to regression, very little unexplained variation, which is why it's freaking significant. Plus, we have a really large residual degrees of freedom. But when we make a graph of this, and this is the crudest of all graphs because I haven't really prettied it up at all, what you see is that you see a cluster of points down here, which is winter Oklahoma City. You see a cluster of points here in the middle, which is winter Galveston. And you see a big cluster of points up here because this is both summer Galveston and summer Oklahoma City. So that's not necessarily what you want to know, because there are plenty of these individuals in here that are not thermoconforming. And so what you really want to do is you want to do regressions on each population season combination separately. So we can get the summary of the regression for body temperature versus wall temperature for winter Oklahoma City, and you see that the slope is relatively low. But what you want to do is you want to use the linear hypothesis code to test against a slope of 1. And when you do that, you find that that is significantly different from a slope of 1. So it's below 1 because the slope value, and you'll see that I oftentimes will make notes to myself of what the observed slope value is. So when I ran the code up here, I got a slope of 0.5839. I'll put that in there just so I don't have to go back and rerun code in order to look it up. I can just actually open up the script and the results is there. So we find that this is a slope that is significantly different from 1, which would mean that these animals during winter are not thermoconforming. They're just cold is what they are. When we look at winter Galveston, the slope is 0.42. Once again, we should be very surprised if this is also not different from a slope of 1, but it isn't different from a slope of 1 as it turns out. And that's probably because we have relatively low sample sizes as much as anything else.
Dr. Kowinski?
Yeah.
So you compared each season with population to the slope of 1.
Yes.
But do you ever go back to compare the slopes to each other?
I don't in this case, because the question that the researcher had is, do these geckos thermoconform? And if they do thermoconform, it basically means that their body temperature is the same as the wall temperature that they're sitting on. And so the hypothesis here isn't, is the slope different from another slope of another population? The question is the slope of the line a slope of 1? Because a slope of 1 basically means that body temperature is equal to wall temperature.
Okay, so we have to go back and delete that stuff and just compare each
it's the
individual
body condition data that you're wanting to compare one population season to another population season. And I'll get to that in a few minutes. Okay. So for all these things, you just have 4 comparisons, and each comparison is the slope that you observe to a slope of 1. So you can do the regression of body temperature on wall temperature for summer Oklahoma City. You find that that slope is higher, 0.8. And when you compare that to a slope of 1, you find that that slope is not different from a slope of 1. And here you find for summer Galveston a slope of 0.62. Once again, that slope is higher. And in this case, you find that it is different from a slope of 1. And once again, this is probably due to sample size. You have many more individuals in this regression than, for example, you did in, there are quite a few in that regression also. So always be paying attention to degrees of freedom, because that's going to be useful to know. And this will become this will become more important in a few minutes when we get to the body condition data. So when you present these data graphically, you kind of want to do something that's a summary. And so what I did in this case is I used facets to basically divide the data into summer and winter, and then I used color to tell me the two different populations. Galveston is red and Oklahoma City is blue. And so you can see that for each of these, there is a line of best fit. The line of best fit here is not very good for the Galveston winter population. There's a lot of residual variation around it, which is probably why the Galveston winter data didn't look different from a slope of 1. So if we go back to winter Galveston and rerun this model, we see two things. We see, one, that the regression isn't significant to begin with, which means that that slope is not different from a slope of 0. And when we test it against a slope of 1, it's also not different from a slope of 1. So basically, you can't distinguish between perfect thermoconforming and total lack of thermoconforming. And it's just because a couple of things. One is you have relatively low sample sizes, and the temperatures that you do have are very variable, which is not the case in all of the other conditions here. So winter Galveston is a little bit of an anomaly. One of the issues is that it spans a relatively narrow range of wall temperatures, and within those wall temperatures, body temperature varies quite a lot. So figure out some way of graphing it in a way that kind of distills things. This was the way that I went about doing it, is by using facets. So I've talked about facets before, we've used facets before, but this just basically divides your data up into a grid. In this case, it's just 2 columns, and they're divided up by season. We could have just as easily colored the seasons and done a facet with population instead. And in this case, it would look like this, where summer is red, winter is blue, and in Galveston, you see that the winter numbers are not that different from the summer numbers, although you still see that wide confidence interval around the line. You see that Oklahoma City has very different summer winter things, but we've basically just divided the data up into Galveston versus Oklahoma City and grouped our data here by season. You could do it either way. If you wanted to, and this is maybe a less productive way of doing this, you could facet by season and population. This would give you 4 different graphs. Each graph would be a combination of Galveston, of a combination of population and season, population and season. So Galveston summer, Oklahoma City summer, Galveston winter, Oklahoma City winter. But once again, whatever works for you. You could actually make the lines appear differently if you wanted to, by making them black so that they stand out from all the background. So you can see what those lines are. You can see that I've made the data points transparent, 50% transparency. That's what alpha is about, so that you can see where individual data points are overlapping with one another. And so anyway, the order of things matters because it plots things in the order that you give it to them. And so if I moved Geom Smooth in front of Geom Point, and this is hopefully something that you just kind of picked up as we went along, you'll see that these points will overlap the line and makes the line harder to see. And so I generally put my line last so that I can see the line if the line is important to me. So anyway, lots of different ways in which you can go about this. One of the things that I like about facets is that when you use facets, it makes the X and the Y axis the same for all of your graphs. And so in terms of interpreting data, it's nice to have your axes all the same. And in facets, you don't have to go and set that. If you were not using facets, you would have to set whatever the Y limits and the X limits are for all of your graphs in order to make all of your graphs comparable to one another. All right, body condition data, I think, is probably what has been causing you the most grief. Unfortunately, the body condition data are in a whole different data file, so that instead of season, it's collection, and instead of population, it's pop. So what I did, just to kind of keep things straight for myself as I went through this, I just renamed what was collection is now season, what was pop is now population, so that I have kind of parallel treatment in my script from one to the next as I move from temperature data to body condition data. And you can see that it has renamed collection is now season, and what was pop is now population. Have to do the same thing here. Pay attention to two things. Pay attention to total sample size. This is winter Oklahoma City. We have 44 observations. We have winter Galveston. Once again, winter Galveston, we have 64. So in this case, we have radically different sample sizes among these different subsets. For summer Oklahoma City, we have 37 observations, summer Oklahoma City, and we have summer Galveston. We have 43 observations in summer in Galveston. So when we look at these data, there's a problem that I hadn't foreseen. One of which is that there's another species of gecko in here in all of the Galveston populations, which I forgot that it was in there. In Galveston, there are two species of geckos. And so actually one of the things that we need to do is we need to filter better than this. And so we need to filter out the Certipodian. I did not foresee this. I'm gonna have to go and remind myself of how to exclude things in filter. Choosing subsetting. Oh, I know how to do this. Never mind. Blah. The easy way to do this is going to be we only want Hemidactylus tursicus.
Dr. Glowinski.
Yes.
What about making this report our final?
No. Thank you for that suggestion, though.
Are we only going to have one day to work on the live coding for the ANCOVA?
You mean on Friday?
Yeah.
In theory, we might get to it here in a few minutes because I'm about to be done with what I just did. So, yeah, so what I needed to do to this filtering thing is to add Hemidactylus tursicus to it. So I need to add this little thing to each of these because I forgot that there were 2 species in this data set. And once I've done that, you can see that it just has Winter, Oklahoma City, and just Hemidactylus tursicus. Winter, Galveston, and just Hemidactylus tursicus. Winter, Galveston, and just Hemidactylus tursicus, blah, blah, blah. So this is the part that I wanted to get to, actually. When we run this analysis here, this is basically just, I'm going to name a new analysis here. It's weight versus snout vent length with the Winter Oklahoma City data. And when I get that, now my slope value hasn't changed at all because Certipodium scabrum doesn't live in Galveston. When I do the Galveston analysis, I'm going to find a different slope value because the slope value does change because I had 2 species in there, 18735. So, and I have 44 geckos in Oklahoma City and 61 geckos in Galveston. I'll do the same with Summer, Oklahoma City, which shouldn't change because there's only 1 species there, and Summer in Galveston, which will change because there are 2 species there, although I didn't change it by much, 728. So now I've run each of these models. So now you want to compare populations to one another. So let's say that I want to compare Winter Oklahoma City with Winter Galveston. So 2 populations in the winter. Well, I can do this one of 2 ways. I can use the model of Galveston that has the larger sample size. So this has a sample size of 61. The Winter Oklahoma City data has a sample size of 44. If you compare the Winter Oklahoma City slope to the Galveston model, it's going to give you a highly significant difference, 8.153 times 10 to the minus 5th. So that is a p-value eight, 1, 2, 3, 4, 5. So this is the p-value for this comparison. Highly significant, those 2 slopes are different. Which when you graph the relationship between weight and snout vent length, it should be apparent to you. But watch what happens when we compare the Winter Galveston slope to the model for Oklahoma City. Remember that the Oklahoma City data has fewer geckos, fewer observations in it. We still get a significant result, but this result is only significant at the 0.002 level. So what's different about the way you're making the comparison is in this case, you're comparing a slope that is based on 44 observations to a model that is based on 61 observations or whatever it was. In this case, you're taking a slope that was based on 61 observations and you're comparing it to a model that is based on 44 observations. Because you're comparing this slope to a model with a smaller sample size, it's harder to tell those slopes apart because this has a lower R-square value probably than the model with 44. Let's go back and rerun these. So R-square of 79 versus an R-square of 82. So as you go through and make these comparisons, it's good to always compare the slope that you generated from the small sample size subset of your data to the model that was generated with a larger sample size. In most cases, you'll get qualitatively the same answer, but in some cases, you'll get a qualitatively different answer, and in all cases, you'll get a quantitatively different answer. Now, when I look at your reports, I'm going to do all of the different ways of doing it so that I can evaluate your numbers correctly. But my advice would always be to use the model with the highest sample size as the model you're comparing a given slope to. So if I was doing this for Winter, Oklahoma City, I would actually compare the slope of Winter, Oklahoma City to the model of Winter, Galveston. To do this for Winter, Oklahoma City versus Summer, Oklahoma City, I would go up here and say, well, which one of these has the highest sample size? Well, Winter, Oklahoma City has a higher sample size than Summer, Oklahoma City. I would actually take this hypothesis and just copy it and paste it down here. And I would compare the Winter, Oklahoma City model to the slope from the Summer, Oklahoma City model, which is 0.1536.
So the one with the largest sample size goes in the front, goes right there.
Yep.
Okay.
So that shows that it's not significant. If we do the same thing, but we compare Summer, Oklahoma City to the Winter, Oklahoma City slope value, which is already in there. Whoa. It helps if you know how to type. You see it's still not significant, but it's even less not significant because you're now comparing this slope value to the lower sample size model. So once again, the same qualitative result, they're not significantly different, but a different quantitative result because we're comparing a parameter estimate to a model with less power, as opposed to comparing a parameter estimate to a model with more statistical power because sample size is higher. Does that make sense?
So since the p-value is significant, then it means...
Nope, in this case, the p-value is above 0.05, so it's not significant. These two slopes are not significantly different.
Okay, so it's not significant. So like when we put that in our write-up, like what does that mean?
So in this case, so for the Winter, Oklahoma City situation, you have a p-value that is really tiny, which basically means that the slope of, let me write this up on the board. This is why I write these things in comments so I don't have to go back and regenerate them. Eight, 7, 3, 5. So this slope of 0.14733 and this slope of 0.1087, these are different from one another at a really high significance level. This slope is steeper than this slope. And when you go and look at the data, I showed you this graph earlier. This comparison that we just looked at is winter, Oklahoma City versus Galveston. Those two slopes look different to the eyeball, and when we test them, they are different because the winter Oklahoma City data has a steeper slope than the Galveston data. And that is what we just verified quantitatively by comparing the slope generated by the Galveston data to the slope we observe from the Oklahoma City data for winter. Okay, so once again, the results that you get here should comport with what you see in a graphic. Also, when you look at this slope for winter Oklahoma City and this slope for winter or for summer Oklahoma City, if you had these two sitting next to one another, those slopes look fairly similar. And once again, when we go and test to see if those slopes are different, we find in both ways of doing the test that they are not different from one another. And so, once again, the results of your statistical test should, once again, conform to what you observe, in this case, in graphs of the data. So this is the kind of figure that you would want to be creating, a figure that shows you the slopes of the lines relating weight to snout vent length for both Galveston and Oklahoma City, and for both winter and summer. And once again, it doesn't really matter how you facet it, but you can look at this slope, the blue slope here and the blue slope here, and you can see that those are fairly similar. The question is, they look similar, are they actually statistically different from one another? And in this case, they are not, because the p-value is above 0.05. But what the p-value is, I've talked before about how p-value is as much a function of sample size as it is a function of difference. You have a different p-value here, a lower p-value here, because you're comparing to a model with more degrees of freedom. Here you're comparing a model to a slope value to a model with fewer degrees of freedom, and as a result you have a higher p-value. That's not because the difference in slope is any different, it's just that in one case you're testing it against a more powerful model versus testing it against a less powerful model in terms of the ability to distinguish between these slopes. Which is why you should always compare the observed slope to a model with higher sample size, because that model with higher sample size will give you more statistical power to see a difference if there's a difference there. Does that make sense to everyone?
So I have a question about like when we're reporting all of these.
Yeah.
So you talked earlier about putting like regression data into a table of some sort.
Sure. Yep.
And I just want to clarify, a few weeks ago you said that when we report regression data, all we need to report is like the equation for the line, the p-value, and the r-squared. Is that true? Okay, so just like make columns for that.
So you can do something like that, but for this thing that we're doing here, so I would like at some point to actually see, I would like to see at some point in your report these kinds of data. what is the slope value? What is the y-intercept? What's the r-square value? What's the f statistic? How many degrees of freedom is on that f statistic, and what the p-value is? You can easily put that in a table that shows, because you ran 4 regressions, you have 4 lines in that table, 1 line for each regression. But for this thing that we're doing right here, a useful thing to do would be to have a table kind of like this, where you have winter Oklahoma City, winter Galveston, summer Oklahoma City, and summer Galveston. And then one of the things that you can do is you could leave the slope values here. Actually, I should have moved this all over. Since you're comparing slopes, so you have 2 populations in winter, 2 populations in summer. You have Oklahoma City and Galveston, and Oklahoma City and Galveston. You have whatever the slope values are. And one of the things that you could do in preparing a figure that makes it quick and easy for people to understand is put brackets out here, and then just stars for how significant things are. A bracket here, you know, not significant. A bracket here that is not significant. A bracket here that is going to be not significant. So you can use brackets to say, well, this comparison is highly significant. This comparison is not significant. This comparison is not significant. So that you kind of give me a graphical way of sorting through all these comparisons. These are 1, 2, 3, 4 comparisons. There's one other comparison, which is Oklahoma City winter to Galveston summer, and Galveston winter to Oklahoma City summer. And this one is going to be highly significant. This one is going to be not significant, if I recall the results. So something like this, you could also do this in a matrix form, where summer Oklahoma City, well, let's do them the way I think of them actually. Winter Oklahoma City, winter Galveston, summer Oklahoma City, summer Galveston. So this would be this many columns. There are lots of ways of doing this. Winter Galveston, summer Oklahoma City, summer Galveston, right? Yeah, so we don't need this last row. Now, this correlation is a correlation of 1, because it's winter Galveston versus winter Galveston. Same thing here, same thing here. But the correlation between winter Oklahoma City and, yeah, the comparison between winter Galveston and winter Galveston doesn't make any sense. You're comparing 2 things that are exactly the same. But the comparison between winter Oklahoma City and winter Galveston, this would be a significantly different slope. So one of the things that you could do in this box here is you could put the slope of Oklahoma City, 0.14733, and the slope of Galveston, which is 0.108, whatever it was. And then you could, you know, color code that red for being significant or something like that. And each of these would have your 2 slope values that you are comparing with one another. And it has all possible combinations. So 1/2 of this graph would be just blacked out. You would have, is the slope of winter Oklahoma City different from summer Oklahoma City? Yes or no. Is winter Oklahoma City slope different from summer Galveston? Yes or no. So there are a variety of for the reader, easy ways of thinking about the data that you, a statistician, can think through and say, okay, there's a lot going on here. How can I present that to the reader in a way that it's easiest for the reader to grasp? Does that make sense?
Kowinski,
Yeah.
Yeah.
this perfectly makes sense. I understand the changes you've made in the assignment. Although I also think that this increases the amount of work that we already had into the report. So
But it isn't a change in the assignment. It's the same assignment it was before. I'm just now giving you some help coding.
Yeah, absolutely. But regarding yesterday, you told me some different things, and I worked that different things.
Yes, because you mixed me up talking about temperature and body condition all in the same conversation.
I mean,
so,
I'm
yes.
sorry. Yeah, but
no, it's not a problem. I should have been quicker on the uptake when we were having that conversation.
Well, what I'm trying to say is that I have like a lot of work for another classes as well. Can the assignment be extended to Friday?
I don't have a problem. Does any of the other class have a problem with that? I realize some of you are done and you just want to be done.
I mean, the ones that are done, they're already done. I'm not done. I'm not quite yet done.
Does anybody have any objections to extending until Friday?
That's fine by me.
All right, hearing no objections, then I'll just extend it until Friday.
Thank you.
Yeah, so is this now all clear? And is it nice to see some code, some script that helps you with this?
I think so.
Okay. All right. Questions about the analysis of covariance?
I've got some questions, not on the, well, I have some questions on the report that's due, but back the example one that we had, the big long example where we had all the different plots and stuff, all that good stuff. Towards
I've got it right
towards
here.
the end, yeah, you shift into the post hoc tests.
Yep.
Like the Shapiro.
Okay, so Shapiro-Wilks test is a test of the assumptions, not a post hoc test.
Oh, okay.
In theory,
yeah, okay, fine. The test of the assumptions
that
are in the back of all that code.
Yep.
Shapiro, we're looking for a p-value greater than 0.05.
Yeah, because you want to see that they are not different from normal is what you're looking for.
Levine, we're looking to make sure that variances are similar.
Yep.
Same thing.
Again,
We're looking for a p-value. Same thing. Looking for a p-value greater than 0.05.
Yep.
The next one, it's a new one. You're checking to see if the treatment variable is independent from the covariate.
Yeah. So
and so, what are you looking for in a p-value there?
Once again, you want those things to not be different.
So you're looking to, well, see, now I get confused. If you want them to not be different, let me write that down. Want to not be different. But that would mean, can you restate that using the word independent? You want them to be independent?
Yeah, so let me go and give you an example of this. So if you look in the
okay, but if you're looking for them to be independent, you press the button, you get an ANOVA table, and you're just looking for a p greater than 0.05
Yep.
or less?
Yep, same.
Okay.
So let me show you what that looks like. In the Gecko data, the X variables are relatively the same across all combinations of this thing. So winter, summer, Galveston, Edmond, Oklahoma. They all span the range of about 30 to about 60. 30, 60. They're a little shorter in Galveston than they are in Oklahoma City, but they largely overlap. In the analysis of covariance example that this book chapter from Packard and Boardman, once again, you see that the measure of size here largely overlaps between these two data sets. A situation where they don't is a situation like this, where one treatment has all small individuals and another treatment has all large individuals. In theory, that complicates things because it's difficult for you. The grand mean of the covariate may lie outside the range of values that you have for a regression. So the reason that this becomes complicated is that whenever you calculate the 95% confidence interval for a regression, and you see these in the gray bars around a regression in R, you will notice a couple of things about them typically. Is if you have a bunch of data points, you have the best fit line, but then the confidence intervals typically do something like this. The confidence intervals are tighter in the middle of the range of values than they are out here at these ends. And the reason for that is that you know something about the values inside of this narrow range, but you also know something about the values outside of that range. And so you can have a great deal more confidence in the slope in this area than you can out here. In this area, you have some confidence about values lying to the inside, but you have no idea what this relationship does outside the range of your own data. So now, if you're doing an analysis of covariance, and one data set has this relationship in reality, another data set has this relationship in reality. They're not linear, but for whatever reason, your sample, I should have drawn it this way, but for whatever reason, your sample only includes those data. It would look like this has a slope of this, this has a slope of this. The grand mean is somewhere in here. You would then move all of these data points up to that grand mean. You would move all of these data points down to that grand mean, and it would ignore the fact that this relationship actually flattens out here, and this relationship actually flattens out here, because the way you sampled, you missed this portion of the relationship between the predicted variable and the covariate. And so it's always a bad idea, and this is why it's one of the assumptions of an analysis of covariance, to compare two treatments that don't have overlapping covariates. So this situation, not good. This situation, not good. Because you don't have any idea.
Paul, are you sharing your screen? I don't see.
Oh gosh, I'm not sharing my screen. I forgot to flip that back on. Sorry.
I have all Paul.
All Paul all the time.
All
that's terrible.
There we go. Okay.
Yeah.
Okay.
So this situation, because you don't have any idea of what the closed dots are doing in this range, and you don't have any idea of what the open dots are doing in this range, it's difficult to make the assumption that those slopes are the same. Yeah. Same thing here. You don't have any idea what the closed dots are doing down here. You don't have any idea of what the open dots are doing in this range of the covariate. And so it's difficult to make the assumption that those slopes are actually similar. And so that's why you check to see, does the covariate differ between the two treatments that you're comparing? Because if they don't, the homogeneity of slopes becomes a dicier assumption.
Right. Okay. So you want them to be independent. You want a high p-value
to be not different from one another. Yep.
But I guess I don't understand the English of that. You want them to not be different, but you want them to be independent.
Well, the way they so if the covariate was dependent upon the treatment, then you would have treatments that had different ranges of covariate.
Oh, well,
does that make sense?
No, yes, I buy it. I buy it.
Okay.
Okay. So in this upcoming report, we have 2 covariates. We have to do that analysis twice, right?
You only have one covariate.
And once for the other covariate.
You only have one covariate.
I got rank and I got years. And
rank. So rank is not a covariate. Covariates are always continuous variables. So what you have, and I think I wrote this to you in an email, you have 2 treatments. Let's see. So rank has 3 levels, gender has 2 levels, years is a continuous variable. This is treatment 1, if you want to think of it this way. This is treatment 2. This is a covariate. So you only have one covariate, but you do have 2 categorical variables. You have rank and you have gender. And you can't really put a number on gender. You could code males 1 and females 0, but you could just as easily code females 1 and males 0. So it doesn't really fit the criteria for a covariate. Does that make sense?
So how would you, I mean, in this line, you run the linear model, parentheses, and your example was IQ tilde group. So yeah. you had continuous variable, then a tilde, then your categorical variable.
Yeah, so let's say that you had, in this case, well, okay, so this would be a classic example. So in this case, you have, let's say rather than the data that you have in this example, you have another additional variable where you have the treatment, which is, did you get the drug versus the placebo? So this has 2 levels, but this drug might interact with gender. So you have male patients and female patients, and you want to know if the treatment has an effect on memory score, if there are differences between males and females in terms of gender score, and you have IQ values for both males and females in this situation. So this would be analogous. And so if you had in this data set, I have to go back to the very beginning. If you had gender, a regular ANOVA would look like this. It would be group by gender, and you can't run this because there is no gender in the data set. And this would give you the ANOVA, and it would have a group variable, a treatment variable, a gender variable, and an interaction term. And then if you wanted to do this as an analysis of covariance,
line 363, I think.
Yeah, if you had an analysis of covariance, so this would be, no. Well, let me do this. Find. So this is the analysis of covariance. It is having group and IQ, but you could also just as easily have a second categorical variable in there, both of which potentially vary with IQ. And so this would be the type of syntax you would use to do the analysis of covariance. So what you have here is I've given you an example of a one-way analysis of covariance. And now I've asked you to do a two-way analysis of covariance. Nothing has really changed except now you have a second categorical variable. But all the concepts still apply.
So gender and IQ, those are the confounding variables. Those are the
nope. These are all sources of potential explanatory variation. You have variation due to taking the drug or not taking the drug. You have variation that is potentially accounted for by males being different from females. And then you have a confounding variable, potentially, this covariate, which is IQ. And so these are all sources of potential variation. Remember that the way this will ultimately be analyzed for significance is in an analysis of covariance table. And analysis of covariance tables are structured by source, the degrees of freedom, the sums of squares, the mean square, F, and P. A useful way to think of this faculty salary data is that there is a source of variation in the data due to the rank, 2 degrees of freedom because you have 3 ranks, assistant, associate, and full professor. You have an effect of gender. This is 1 degree of freedom because you have 2 genders, male and female. Then you have the effect of the covariate, which is years of service. This is going to be however many degrees of freedom are associated with the regression having to do with years of service. But because it's just 1 slope value, it's going to be one degree of freedom here. Then you're going to have a rank by gender interaction. Do rank and gender interact? So one of the things that might be true of these data is a number of the faculty who were in this data set at this time period were hired back in the 1970s. So full professors who have been here for really long periods of time, you might expect a bigger gender inequity gap because of hiring practices back in the 1970s. And you might expect to see less of a gender gap in newer hires who are all at the assistant professor level. And so that would come out in a gender by rank sort of interaction. You can also have rank interacting with IQ, not IQ, duh. Rank interacting with years of service. You can have gender interacting with years of service. And you can have actually rank by gender by years of service. And then at the bottom of all this, you'll have residual. Any variation that's not explained by these main effects and all these interactions just goes into the residual category. And so if you were interested, for example, in salary compression, which of these interactions would you be looking for?
You'd be looking to, well, where is it? You'd be looking to see if years
you would be looking for an effective rank, actually. And when you look, when you see that there's an effective rank, you would then want to look at the individual values. You would want to see, well, what's the difference between assistant professors versus associate? You would want to look at the difference between assistant professor versus associate professor. That's going to be a certain magnitude versus the associate professor versus full professor. If there's gender compression, you should expect the adjusted mean of assistants and associates to be a certain distance apart, and you should expect the distance between associates and fulls to be less different.
So you'd read it on the rank line if you're looking to see if there's salary compression. On the rank line, you'd read across and see if it has a significant p-value.
Yes, and if it does, which it will, because you get a raise when you advance from assistant to associate to full professor. So you should see an effect, a significant effect. This should be significant.
Okay.
So then to determine whether compression is happening, you need to do some pairwise comparisons. Is the gap between assistant and associate large relative to the gap between associate and full? If these gaps are about the same, then there's no compression. The gap from one rank to another is consistent across all ranks. Does that make sense?
So you're saying if we see that the gap, the final question is the gap between assistant and associate similar to the gap between associate and full?
Mm-hmm.
Okay. Now, can you drop back and describe what you think salary compression is? Because it's clear it's not what I think salary compression is.
Yeah, so salary compression as defined in academia, what happens is you're hired at the rank of assistant professor. Let's say that you're hired at $42,000 a year. Then when you move to associate professor, you get a $2,500 a year raise. So you're now at $44,500. And then when you get when you get promoted to full professor, you get another $2,500 raise so that's $47,500. So in all these cases, there's a $2,500 gap between ranks. There is no salary compression because everybody's different by the same amount. But once you get to full professor, you don't have another promotion. There's not a fuller professor or a fullest professor or a super awesome great professor who extends deadlines for assignments to Friday because he didn't probably provide you as much information as he could have. There's no other rank to advance to. So once you reach this level, all you get are the standard cost of living adjustments that everybody gets. You don't ever get this big bump in salary. Not that $2,500 is much of a big bump in salary, but these gaps are always the same. Now, when I was hired, the going rate for faculty member was about 38,000, which means that this would be 40,500, which means that this would be 43,000. This was the year 2000. I was department chair for a while, and I know that right now we have to hire in faculty members at about 47,000. Because that's just the going rate for assistant professors. As this has changed from 38,000 to 47,000, nothing has changed up here. And so now the gap between assistant and associate is such that new assistant professors are potentially being offered starting salaries higher than the starting salaries of or the salaries of associate professors who have advanced through the ranks here, and higher than full professors who have advanced through the ranks here. And so what happens is salary gets compressed. The low end gets closer to the high end over time, because while you have to bring in new faculty who require higher salaries, you don't have to offer commensurate gains in salary to those people who are already here. Does that make sense?
Yeah, it's whether cost of living increases for the current employees keeps up with the hot job market that you have to pay for a new person.
Yeah, they don't ever look at, and this is one of the concerns, they don't ever look and say, well, we hired Dr. Kowinski back here at 38,000. What would his salary at full professor now be if we had hired him at 47,000? Well, it would be considerably more than it currently is, because I would have gone through these steps of advancement, plus I would have started at a larger salary. So every year when we hire new faculty, we don't hire those faculty at a set rate and then correct all of the other salaries at the institution based on that base salary now.
So statistically, how would you compare those two $2,500 brackets?
So the way that, so statistically, how would you compare this? That's actually trickier. What I would do for this report is I would just look at those gaps and say, and
visual judgment call. Okay.
Make a qualitative statement. Here you see that the gap between associate and assistant is this big. The gap between assistant and full is this big, after correcting for differences in years of service, because all the full professors have been around for forever.
Right.
And can't get rid of those bastards as much as.
What are you comparing? The lowest full professor to the highest associate professor?
No, you would compare the adjusted means.
Okay.
So you would need to extract the adjusted means and say the adjusted mean for assistant professors is this, the adjusted mean for associate professors is this, the adjusted means for full professor is this. Are those gaps similar or are they not?
Okay.
We know that the pay is going to be different, because you should be paying full professors more than assistant professors. The question is, how are those gaps distributed? Does that make sense?
It does. Yeah, that's a different concept of salary compression then.
Yeah, how do they define salary compression in your field, Tom?
It's you take people that have most recently been hired in the current hot job market, and you compare it to people that had just most, let's see, what's the right way to say, who were one step less removed from being recently hired. So it's like you would compare the people that were hired this last year in the current hot job market compared to the people that were hired in the last in 2 to 5 years ago.
Yeah,
because those the 2 to 5 years ago hires are the people that'll be offended by salary compression. They'll see somebody who's 1 year more junior than them being paid $6,000 more.
Yeah, well, okay, so the same thing. It's the same concept.
And it's because the hot job market.
It's the same concept. It's just that in academia, where you may spend 30 or 40 years in your position, the time frame for what constitutes recent hire is different. I think one of the faculty in that survey was here for 42 years, and so like that's longer than most people keep their jobs in any corporation nowadays. So it's a very similar idea. It's just that the time frame for comparison is wider because of the nature of academia. Oh my gosh, it's 9 o'clock. On Friday, we will talk about ANCOVA totally. So come with your questions regarding the next assignment. And in between, email me if you want to meet up and talk coding for that and things like that. We can set up Zoom meetings. We can go back and forth via email. Sometimes it's actually just as productive to meet in person where I can see your screen and work you through things that are giving you problems. All right. I will see you guys on Friday then. All right.
See you.
Yep. Brooks, did you say something? Yep, you're gone. Everybody's gone.